Namaskar and welcome back to another lecture in our continuing series, Development and Applications of Special Concretes. Today we'll start our discussion on another special concrete, the fiber-reinforced concrete. Getting started with fiber-reinforced concretes, let's talk a little bit about why they are needed, what kind of fibers are used, and the basic issues involved. So the development of fiber-reinforced concrete attempts to address the following two deficiencies in cement-based composites. One is a relatively low tensile strength, and the second thing is low energy consumption capacity, which is called toughness. Now this toughness parameter is something which is used to characterize material. From a construction engineering point of view, this is useful when we are talking of performance of structures in earthquake loading, where we expect the structures to show a lot of energy absorption capacity. Typical uses of fibers in cement-based composites could be for shrinkage crack control and mechanical property enhancement. Now these mechanical properties could include flexural properties, impact resistance, and to alter the failure mode, as we will see. This here is a diagrammatic representation of how fibers are incorporated into the concrete matrix. Remember that as far as concrete is concerned, we know that it is a composite made of cement, water, sand, and aggregate. Aggregate here refers to coarse aggregate. So I'm not using the word coarse, I'll just simply write it as aggregate. Now in this normal concrete, we add fibers. Now this picture here shows two types of fibers being used. This is the matrix of concrete. One is continuous fibers and the other is discrete short fibers. So these long fibers are continuous. So this could be again reiterated as long continuous fibers. And here we have short discrete fibers which are oriented in random directions and distributed throughout the matrix. Fiber reinforcement versus conventional reinforcement. Now that's something which often comes to our mind, that okay, how is fiber reinforcement different from conventional reinforcement? We know from our discussion of reinforced concrete members that if we have a beam which is simply supported, let's say, and we subject it to a loading here, this portion of the beam will develop flexural stresses in excess of the tensile strength of concrete, and we will have flexural cracks. Now once these flexural cracks are formed, in order to arrest them, in order to make sure that they do not propagate through the section, we put reinforcing bars. So this is our understanding of reinforced concrete. Now from this understanding, how is the fiber reinforcement different? Now this slide seeks to explain precisely that. Fibers are generally distributed throughout the concrete, whereas reinforcing bars or wires are placed only in predetermined locations. So as we can see in this slide here, or in this picture, reinforcing bars are placed at the tensile face of the member. We put some reinforcing bars on the compression face itself also, but it is all at predetermined locations. Whereas fibers are distributed throughout the matrix. That is, if I was to use a different color here, fibers will be all over the place as far as the matrix is concerned. So it's not at a predetermined location as in the case of reinforcing bars. Fibers are relatively short, discrete, closely spaced, and randomly distributed throughout the matrix. These reinforcing bars are long bars. They run throughout the length of the member. How much of it runs through, how much of it is not running through, there may be some curtailment and so on, but by and large the principle is that these are long bars. They will run throughout the section. Whereas in the case of fibers, that's not the case. They are short, discrete, and randomly distributed throughout the matrix. Presence of fibers in concrete modifies the properties of the concrete per se. So remember that we had a picture which we use all the time, that we have concrete and we have this is coarse aggregates and we have this as my mortar matrix. These are the coarse aggregates. So this is the properties of this picture we use to explain the properties of concrete. And you would recall that we use some kind of a three-phase material model where we said that the concrete could be modeled as made up of the mortar phase, the coarse aggregate phase, and the transition zone. So based on this, we had explained the properties of concrete. Now, the presence of fibers in concrete modifies the properties of this concrete. That is, because these fibers, now let me use another color here. Now the fibers here are all over the place. Of course, they will not enter the coarse aggregate as I've shown here, but they are all distributed in the mortar, and it's in 3 dimensions throughout the concrete or throughout the mortar. So this presence of fibers modifies the properties of the concrete itself. This does not happen in reinforced concrete. In reinforced concrete, we have concrete and we have reinforcement. Whereas in fiber reinforced concrete, obviously, as it's stated here, fiber reinforced concrete could very well be used as the concrete to be used in a reinforced concrete structure. That is, then we will have fiber reinforced concrete being used as part of the conventional reinforced concrete. That is, then we will have a section here which will have reinforcement, and as far as this is concerned, instead of concrete, we will have fiber reinforced concrete. So there's nothing wrong with that. So fiber presence, or the presence of fibers in the concrete matrix, modifies the properties of concrete in different ways, whether it affects the compressive strength or not, whether it affects the tensile strength or not, whether it affects the modulus of elasticity, whether it increases the toughness, and so on. So those are all questions that we will answer as we go along when we deal with the impact or effect of fiber addition on the properties of concrete. And that would become the properties of the fiber reinforced concrete. Having said that, it is a different composite. It is not conventional reinforced concrete. Conventional reinforced concrete, the way the image is normal concrete with reinforcing bars placed at predetermined locations in order to primarily control or augment the properties of concrete in tension. Moving forward, the main factors that control the performance of the composite material are the physical properties of the fiber and the matrix. So obviously, when we are talking of the matrix, which is in this case the way I've shown here, this is my concrete, and we have some fibers. So the properties of this composite obviously would depend on the properties of the fiber and the amount of fiber we use, and of course the properties of the composite, that is the properties of the concrete. The strength of bond between the fibers and the matrix. This is something which we will shortly see as to what happens if we want to create a model of how this fiber participates in modifying the properties of this concrete. So the bond becomes a very important characteristic, and that's something which needs to be investigated. It needs to be studied in greater detail. So the long and short of it is that the performance of this composite called fiber reinforced concrete will depend upon the properties of the matrix, which in this case is concrete, and the properties and the amount. Of course, you cannot just add one fiber to the concrete and say that you've made it fiber reinforced concrete, or for that matter, if you put too much of fiber, there are other issues. So there again has to be a balance as to how much fiber you can put in, what kind of fiber you put in. So it's amount and the properties of the fiber that is involved, and of course the properties of the matrix and the bond between the fiber and the matrix. So this is pretty much similar to the discussion that we had between the role of the coarse aggregate versus the mortar phase and the ITZ. So these three were the pillars on the basis of which we discussed the properties of concrete. Now with the addition of fibers in that concrete, we are talking of the properties of fibers, the properties of matrix, and the bond between the fibers and the matrix. So as far as the fiber volume ratio is concerned, this picture here just gives you a very rough, very simple schematic representation or a discussion of how the properties of the composite are determined. If the ratio of the fiber volume is VF to the total volume of the fiber reinforced concrete, at a low VF, that is, if the volume of fibers is low, the addition of fibers contributes mainly to toughness alone. There is not so much of a contribution to the strength. At a higher volume fraction, however, the tensile strength of the matrix can also be enhanced and the failure mode can be changed. Now, we will see it later that I can have a material. Let us not bother about fiber reinforced concrete. Let's talk of a simple material. We can have a material here which is going to fail somewhere here. So this becomes the strength of this material. We can have another material which will not fail here but will sustain some more load, sustain some more deformation, I should say. We can have another material which has the same strength, that is, it cannot take any more load than this, but does not fail here in a brittle manner, but sustains a larger deformation before it fails. So this is a very different characteristic. This is what we would refer to as toughness and probably define it in a much more rigorous manner. And then there is always a possibility of a third situation where the material strength is also enhanced. So from here, the strength goes up to this point. Whether or not it leads to any substantial change in the strain capacities or so on is a different story. But here we have three models: the strength enhancement, the toughness enhancement, strength enhancement and toughness enhancement. So as far as fiber reinforced concrete is concerned, what happens is that at low volume fractions of fiber addition, we typically get only this. At higher fiber additions, of course, we also try to get something here. So we have an increased tensile strength and also the corresponding increase in the toughness values. The properties of the matrix influence the bond with the fibers and the mechanical properties of the fiber reinforced concrete, and fiber reinforced concrete can be modified using mineral admixtures such as fly ash, slag, silica fume and metakaolin. So this modification here is for the modification of the matrix properties. So of course, if we change the matrix properties, the properties of the fiber reinforced concrete, which is the composite, will obviously change. Now, as far as the classification of fiber reinforced concrete based on fiber volume is concerned, if the volume fraction is less than 1%, we often call it low fiber composites, and that application is largely for shrinkage cracking. When it comes to moderate fiber composites, typically we are talking of volume fractions which are 1 to 2%, and there we can exhibit or expect certain improvement in the mechanical properties. This can also be used as secondary reinforcement, but only when it exceeds about 2% can we expect high performance fiber reinforced concrete. And there we can have improved mechanical performance and exhibit some kind of strain hardening behavior due to the high fiber content if it is more than 5%. Now these numbers cannot be hard and fast rules or cannot be prescribed with too much of rigor, for the simple reason that the change in properties also depends on the nature of fibers being used. So if you're using steel fibers, you're using glass fibers or aramid fibers, these numbers could be quite different. So the principle involved is that what you achieve would depend on how much of fibers you put in. We could be looking for shrinkage cracking control. We could be looking at marginal improvement in mechanical properties. We could be looking at high improvement in mechanical properties, and therefore we need to add the adequate amount of fibers into the system. So the reinforcement of concrete by discrete fibers is shown here once again. So as I tried to show you in a more rough manner, of course this is equally rough. You can imagine that this is my coarse aggregates. These are the fibers that we are talking about. These are some kind of voids which are there within the concrete. They are always present. And this is my mortar matrix. So voids and micro cracks serves as crack initiators as far as concrete is concerned. The presence of fibers prevents the crack elongation and propagation and increase in crack width, and that leads to an increase in strength of the fiber reinforced matrix by the fiber spacing theory. So now what is being said is that suppose there is a void here. Now if this void was to try to progress, if the crack is initiated at this end of the void, it will soon hit the fiber. It cannot go through the fiber very easily, and therefore it will get arrested. Similarly, if the crack propagation was to happen at this end of the void or this end of the void, then these fibers would arrest further growth, and that also tends to hold on or reduce the crack width that we see. However, having said that, I'm leaving it to you to just think as to what will happen, the kind of qualitative explanation which I have given. What will happen if the crack propagation happens at this location A of the void or this location B of this void? Will this fiber be able to resist the crack propagation? The answer obviously is no. And that is why we need to ensure that there is a certain amount of fibers which are present. We cannot control all the cracking, but we can arrest some of them. Here the fiber will fail. It will not be very effective. Yet another question for you. The presence of these fibers also would alter the properties of my mortar from a fresh concrete point of view. And now as far as the discussion of the placeability of fiber concrete is concerned, it's not simply the placeability of mortar or concrete that we are talking about, but that modified because of the presence of mortar. I think it is intuitively clear to you, or it should be intuitively clear to you after all the discussion that we've been having for different types of concrete so far, that if I have too much of coarse aggregate here, or the amount of mortar here is very less, then can we add a lot of fibers to it? Conversely speaking, in order to add a certain amount of fibers, suppose we have a concrete to begin with which has 60% mortar and 40% coarse aggregates. Now in this, if I want to add, let's say 2% fibers, can I manage with the same 60% mortar and 40% coarse aggregates? Let's not bother about the 2% where it will come from. I can make it 38, I can make it 58, whatever I want to do. Will this property, will this concrete with 38% coarse aggregate, 60% mortar and 2% fiber have the same properties as one which had 60% mortar and 40% coarse aggregates? The answer obviously is no. It will not. So we need to reduce the amount of coarse aggregates. In other words, increase the amount of mortar content as far as fiber reinforced concrete is concerned to maintain placeability. Now this is something which we'll discuss when we talk about proportions, but I thought with this picture it should be intuitively clear that we cannot just add fibers to a concrete matrix and hope that the fresh concrete properties will not change. Using short fibers in concrete, the fiber length of at least 1.5 times the maximum size of aggregate, considering the ease of fiber dispersion, is what is generally recommended. So obviously in a concrete like this, and this is the picture which we have been using all along. So consider a concrete like this. If this is the size of my coarse aggregates here, if I have fibers which are very small, it may not be very effective. So in order for fibers to become effective, it should be at least about 1.5 times the length of the or size of the coarse aggregate, while a fiber length of 30 mm or more is generally recommended. Now this 30 mm is coming from 1.5 times 20 mm. So we generally use a nominal maximum size of aggregate of about 20 mm as far as reinforced concrete is concerned, and therefore the fiber length of 30 millimeters is often considered a benchmark as far as using the fibers is concerned in concrete. Fibers of about 60 mm have a high reinforcing effect used for slabs. The kind of fibers that we use, what should be the length, what should be the diameter, all that also depends on the member that you're using it in. It could be a slab, it could be a beam, it could be a column. Therefore, in slabs, typically the reinforcements is less. So placing the concrete is easier. So we can use slightly larger fibers. So those are the kind of operational issues that we'll probably discuss it. Otherwise, you have to learn it on your own. So the size of fibers ranges from about say 30 mm to 60 mm. When we say for fibers that they are short, discrete, randomly distributed fibers, how short is short? This question is answered here. Short means 1.5 times the size of the coarse aggregate. That is a benchmark number as far as the length of fibers is concerned. What types of fibers are used in the industry as far as concrete is concerned? Fibers made from steel, plastic, glass and natural materials such as wood or cellulose. They are available in a variety of shapes, sizes and thicknesses, and they may be round, flat, crimped and deformed. So there are different types of fibers which are available to us, and this picture here gives you the different types of fibers: steel, plastic, glass and so on. This picture again is typical fibers: steel fibers, polyethylene fibers, and you will notice that as given in the previous slide, the fibers are not necessarily straight. They are sometimes crimped. They are sometimes bent like this. The way your staples are after they are bent, right? So the staples are, if you recall, something like this, and this end really goes back in after when you staple a document. So we have fibers which are in this shape, hooked fibers, straight fibers. As far as the cross section of the fibers is concerned, it could be round, it could be flat and so on. So these are different types of fibers depending on the manufacturing method, depending on the kind of material that you use. Different types of fibers are available to us for use in concrete. As far as the characteristics of common fibers is concerned, the diameter ranges from 0.05 to 0.5 millimeters. The length ranges from 5 to about 60 millimeters. The aspect ratio, which is the length to diameter ratio, is kept at about 100. In the previous discussion, I had said that in order to be effective, the fiber should be about 1.5 times the size of the coarse aggregate. So there are particular applications where fibers shorter than the coarse aggregate size or smaller than the coarse aggregate size also have a role to play. And there's no reason why we should not use them. As for the diameter is concerned, it's 0.05 to 0.5 mm. So you can see that they are not very large. When it comes to reinforcing bars, we don't talk in terms of 0.5 millimeter kind of bars. We talk of 16 mm, 22 mm, 25 mm, maybe 40 mm kind of bars. So that is what is the basic difference, a very important difference between reinforcing bars and fiber reinforcement. So never confuse between the two. So moving forward, here is a typical illustration of failure of a fiber when it is embedded in a matrix. So what we're talking of here is a fiber of length L embedded in the matrix to the extent of half, that is L by 2 is buried, and we try to pull it out by applying a tensile force T here. Now how is this tensile force going to be resisted? It will be resisted by mobilization of a bond stress between the fiber and the matrix over this L by 2 length, and if D was the diameter of the fiber, then pi times D times L by 2 would be the area over which this bond stress will develop, and if there was a limiting value called tau, then this would become more or less the load carrying capacity of the fiber as far as failure in bond is concerned. If this was very large, then the failure of fiber could occur by the breaking of the fiber, which is governed by the tensile strength of the fiber multiplied by pi d square by 4, which is the area of cross section. So basically, if these two were equal, then we will have an equal probability of the fiber failing in tension or by bond. So that's kind of a thumb rule. That's the kind of simple back of the envelope rule which says that L by D, that is the length to diameter ratio of the fiber, this is what is called the aspect ratio as far as the fiber is concerned. This is related to tensile strength and the bond strength mobilized between the fiber and the matrix. So the aspect ratio of fibers is related to the ratio of the maximum tensile and bond stresses. The third possibility, which I have not discussed here, is that if both these are very strong, the fiber is very strong here in terms of the tensile load carrying capacity and the material here is very strong as far as the bond is concerned, then there is a failure which can happen by the failure of concrete. Now this is something which I'm not covering here, and I'm leaving it to you to think about and reason for yourself as to what will happen if the fiber was very strong and very strongly embedded in this matrix and we still continue to apply this force T. What is the third likely mode of failure? So the advantages and disadvantages of using fibers. Since fibers are generally distributed throughout the concrete, many fibers are inefficiently located for resisting tensile stresses. This is one of the very important disadvantages, that they are inefficiently located for resisting tensile stresses because they are randomly distributed throughout the concrete. And the stresses do not act uniformly across different parts of the concrete. So therefore, only at those places where the stresses are acting, the fibers are being effectively used. Spraying the fibers leads to a 2D random orientation, whereas pre-mixing them during the batching leads to a 3D random orientation. Now, depending on how the fibers are added to the concrete mix, the fibers could be oriented in a 2D random orientation or a 3D random orientation, which also has implications in terms of effective utilization of fiber addition for resisting stresses in the different directions. An efficiency factor to take care of the stresses depends on the fiber length, critical embedment length, and the orientation. So these are some things which you will study if you want to study fiber reinforced concretes in greater detail. Recall that I have always said that as far as this particular course is concerned, we will possibly not be able to create experts in all different special concretes that we are talking about. We will probably be able to just highlight to you some of the issues involved, and then if an opportunity arises to use that material, then of course you know what kind of material to look for as far as literature is concerned and what are the issues involved in using that particular type of concrete or that construction method and so on. Now quickly going through the types and properties of fibers that we normally use. This here is steel fibers. Short discrete lengths of steel with aspect ratios ranging from 20 to 100. Aspect ratio, I told you, is the length to diameter ratio. Sometimes they have hooked ends to improve the pull-out resistance, and of course they have the high modulus of elasticity. Steel fibers, according to ASTM A820, have been divided into 4 types or classified as type 1, 2, 3 and 4 depending on what they are all about. Type 1 fibers are cold drawn wire fibers manufactured from drawn steel wires. Cut fibers or cut sheet fibers are those manufactured from laterally shearing the sheets. Melt extracted fibers are molten metal is rapidly frozen into fibers, and then of course there can be any other type of method of manufacture which would give you the type 4 steel fibers as far as ASTM A820 is concerned. This here shows you a picture of machined fibers. This one here is a picture of cut wire fibers and then sheared fibers. So these are some of the pictures that I've showed you for steel fibers. Then we have, of course, glass fibers, as you can see this picture here. Glass fibers means conventional glass fibers are borosilicate type, E glass, and soda lime silica type, which is A glass. Research has shown that there could be alkali reactivity between the E-glass fibers and the cement paste, which impairs the strength of the composite. And alkali resistant glass fibers, that is AR glass, alkali resistant, are introduced to address the issue. Recall that the concrete that we talk about, the aggregates and the cement paste and mortar and so on, this is a high pH environment. This is something which we've already talked about, this high pH coming largely from the calcium hydroxide generated during the hydration process. Now this high pH here means that any fibers or any material that we introduce in this matrix should also be durable in the high pH environment. This is typically, or this could be sometimes not true for normal glass. And that is why when we are trying to assess the applicability or assess or evaluate a particular type of fiber for use in concrete, we should be careful that it should be able to sustain the high pH and it should not deteriorate because of exposure to high pH environments. A corollary to you, why do we not have such worries with steel fibers? Think about it, and possibly at this onset of the next class, I'll give you the answer for it. I'm sure you already know about it. Continuing with glass fibers, loss in strength and ductility of the exterior glass fiber concrete has been reported. Fiber embrittlement due to infiltration of calcium hydroxide into the fiber bundles is the reason for this mechanical properties loss. And we can reduce this embrittlement by using low alkali cement, use specially formulated chemical coatings, and use microsilica slurry to fill the voids in the fibers. So there are problems and there are solutions to these problems if we are really trying to use one type of the fiber or the other. So in the case of glass fibers, if there's an issue rising out of the exposure to high pH, obviously the first strategy could be use low alkali cement. The second strategy would be coating of fibers. The third strategy could be filling up the voids in fibers. So that's something which as engineers we have to always understand what we want to achieve, what are the hurdles in achieving it, and then how do we go about removing those hurdles. Continuing with synthetic fibers now. Synthetic fibers are man-made fibers like acrylic, aramid, carbon, nylon, polyester, polyethylene, or polypropylene. So as far as polypropylene is concerned, these are most popular fibers and are chemically inert, hydrophobic, and lightweight. There'll be a slide at the end of the discussion today where we'll talk about this weight part a little bit. They are usually in monofilament form and help in arresting shrinkage and subsidence related cracks. Fibrillation of both polypropylene and polyethylene resins provides better mechanical bonding than conventional monofilaments, and they are incompatible with each other and tend to separate. So during mixing, each fiber conglomerates into a unit with fibrils at its end. So these are some of the details that we can be looking at if we are trying to really use polypropylene or polyethylene fibers. Continuing with synthetic fibers, this picture here shows you acrylic fibers and this picture here shows you aramid fibers. So acrylic fibers used in cement boards and roof shingle production exhibit high post-cracking toughness and ductility. As far as aramid fibers are concerned, they have a high tensile strength and tensile modulus. They're stronger than the e-glass and steel fibers. Strength sometimes has different connotation when we are talking in terms of fibers and fiber-reinforced concretes and so on. One is the strength per se, that is the load carrying capacity. The other thing which we talk about in strength could be strength per unit weight. For example, a material such as steel has a certain specific gravity, maybe 7.8. What is the specific gravity of acrylic or aramid or glass? And with relation to the weight that we use, what is the kind of strength that we get? That is the strength to weight ratio that we often use to compare the performance. So the strength per unit weight could be one of the performance parameters that we use to evaluate whether one type of fiber or the other type of fiber is useful to us. Apart from weight, of course, we can use cost. Continuing our discussion on synthetic fibers, this picture here shows you carbon fibers and this shows you wood fibers. Carbon fibers are typically produced in strands, possess high tensile strength and modulus of elasticity. Wood fibers are natural fibers. Wood is reduced to a fibrous mass through a process called pulping. Cooking wood chips in a solution of sodium hydroxide, sodium carbonate, and sodium sulfide gives wood cellulose fibers, and they possess good mechanical properties compared to other fibers. I must warn you that when we are choosing to use fibers in concrete, like we talked about the durability in high pH environment, we should also talk about the durability of these fibers themselves due to exposure to water, exposure to oxygen, and so on. Because it should not happen that the concrete initially has a lot of good characteristics, but in 10 years the fibers lose their strength, oxidize or something like that, and then the fiber reinforced concrete has been reduced to simple concrete. So we must study not only the durability of fibers in the initial high pH environment or the high pH environment alone, but also its exposure within concrete over a long period of time. So whether it's wood fibers or steel fibers or aramid fibers, this is something which we must take note of and make sure in the early stage itself, at the planning or whatever stage when we try to evaluate different fibers. Here is a picture which compares the properties of different fiber materials: steel, glass, fibrillated polypropylene, cellulose, carbon, and of course cement matrix is there only for comparison. So if we talk in terms of diameters in micrometers, steel is 5 to 500, glass, polypropylene, specific gravity is listed here, tensile strength is listed here, and the elastic modulus is listed in this column here, along with the fracture strain somewhere here. So if we look at these properties, these are the facts. Now we need to understand, evaluate these facts on the basis of strength per unit weight. We have not listed cost, which could be in tons or rupees per ton or dollars per ton. Now, if we want to compare the performance in terms of cost, in terms of weight, we are very much free to do that. So I'm leaving it to you as an assignment to find out the cost of these fibers in your neighborhood and try to then understand and evaluate how we can go ahead, or whether as an engineer we should go ahead and use fibers in concrete. This slide here shows you some of the references which you could probably go through in order to have a better understanding of fiber reinforced concrete. And of course, as usual, the list is incomplete, and there is such a lot of more material available on the internet which will help you understand fiber reinforced concretes better. Of course, the discussion today has been limited towards the type of fibers that used, their characteristics, and a simple discussion of how fiber reinforcement actually works. These are some of the things that I've already pointed out to you, and there would be so many other things that you could think for yourself in order to understand the different dimensions that are involved as far as the development or use of fiber reinforced concrete is concerned. And with this, I thank all of you, especially my teachers, friends, and colleagues, students who have helped me understand this material better and put forward. Thank you once again, and I look forward to another discussion with you next time on fiber reinforced concrete.